Hi, good evening. It's been a couple of days since I put out the last video. I think it was of XPS, and now again I thought I'd make a video today since I was free in the late evening. And today we'll see about HRTEM image and how to analyze the lattice fringes in ImageJ software. So there are other software also like the famous Kathan software which is generally used, but I think it's a paid one, and ImageJ is a better free alternative than to it, and easy to use because since we already know much of ImageJ as compared to Gatan, but the procedure in Gatan software is also the same. You just have to do the same analysis, or just the UI is different. What you feel, I've used it, but I don't have it as of now. But I've used it, so the UI in Gatan software is different, but the process of ImageJ and Gatan both are same. So you do by either. If your procedure is correct, then your image analysis would be correct. So there is no preferred software, or that Kathan is a better software than ImageJ. Both are equally good, well and good. So you just have to follow the correct process to analyze the image. So just going to what an HRTEM image may look like. You might have seen such images, or might have taken such images when you took a TEM image or an HRTEM image. So you can see here a large number of straight lines kind of things. These are actually crystal planes what we have here. So suppose I'll just show here. Yeah, suppose this is a plane, then this is a plane. All the bright colored ones are the planes. Then this is a plane, then this is a plane, and this is a plane. So all, and also you can see that all are aligned in the same direction. So these are all one family of planes. Whatever we see here, all these planes are seen to just one family. Here you can see some amorphous region because you see these planes have kind of stopped at here. So maybe this may be a grain boundary, what I can infer. I can't conclude, but I can infer that this is a grain boundary. Then again, these planes are starting here. So we may need to take some other good images or this region if we want particularly to focus on the grain boundary. But since I just wanted to focus on my crystal, so I took only this area. So how do we analyze this? As usual, we have our image software. Take this image into the image. Then I'll tell you two methods to do it. One is this one. What first we before doing anything we set the scale. So we remove the scale, then take a straight line, zoom in here, and as better as possible, you draw a line. And while drawing, hold shift so that your line is straight. See, it goes a straight line either at an angle, so 45, 90, or 0. So you don't have end up something like if I don't hold shift, this is what happens. So better hold shift and then plot this line. You have a reasonably good one, but for your papers or your analysis, I say that you do more zoom in and better scale. So set scale 105. I just put this as 5 and unit is nanometer, and then just okay. So our first scale is set. Then we go back. Okay, so our image here, uh, the method one, what we have. So you can see as I zoom in, the pixels start pixelating and it's not a good image. So take it around this reasonable magnification. First method, you have two planes, plot a straight line, or this line should be perpendicular to the lattice planes, or these are called as lattice fringes in HRTM context. So the lattice fringes and this line should be perpendicular. So I have drawn a reasonably perpendicular line. Now just go and measure this. You can see 0.342. Okay. Second method, I just I don't want to fill this because I want to do further analysis, but you understand this is one method. The second method, you take a few of these lines, do this, same, Control M, then you have here 2.23. Then you can count 1, 2, 3, 4, 5, 6, 7, 8. So this is 8 planes. Go to calculator and then 2 point, sorry, 2.231 by 8. It is 0.278. So you see the difference. It's 0.342, 0.278, and this is nanometers. So you take an angstrom. This is quite different. So the better thing what I suggest is, okay, now another thing, if you don't want to count, or let's say you're not able to count this because of the contrast difference, you can just go to here and then you can plot profile. So you have something like this where the grayscale values are plotted. So you have here, let's say I just want to take up to 2 nanometers, or let's say just 1 2 3 4, 1 2 3 4 5 6 7 8. So 8, and then you have your distance here 2.23. So same, 2.231 by 8. So but this is what I showed you, the differences in the result you can observe. So this is not a suggestible method, but this is also one of the method. The more standard approach is to use a Fourier transformed image. So as you know, this HRTM image is in a real space. Now we go to the uh, reciprocal space or the Fourier space. We take a 50 of this image. This is the same crystal or the same image in a reciprocal space. Then you can see all these dots here. These dots are family of planes, as we know. So we consider one of them. We mask it. So and then we fill this one. Then again go to FFT and inverse FFT. Yes, I want to show this error. Sometimes this error pops up which says that this no pixel has been set to 0 or 250. So filtering is not done, something like this. You just press OK, close this, don't save, and again do an FFT. Again plot a circle around it. When that error comes, after that you have now, if you get that error, you don't do fill, you do clear. So this becomes a black color. When you do fill, it becomes a white color. When you do clear, it becomes a black color. So once your is done, then again we do inverse FFT. So first we took an FFT of this one, FFT of this one, then this came, and from here we got this. But then our planes of interest, this plane, are not visible in this one. You can see we wanted these planes and these are not visible, so we don't need it. We again do the same in a different circle. So 50, we have done this one. Now and now we got our planes of interest. So you can see here, this was the this correspond. So you can do either this or this. So both of them are opposite, and then the same. You just have your z component as a negative one. So these are same family of planes, just one of them is different, either x, y, or z. So anyways, we got this inverse FFT and we got our planes of interest. After this, now comes the part you better zoom in. So now you can see it's a much better image as compared to what we had here. Sorry. So we get a better image here. And then we do, so in here also we have the same one. You can either measure this distance or take and take the whatever, like you can take this as an interplanar spacing, but it won't be accurate. The better thing is you take a set of planes, then do take an average. So first, for that you take an angle line, and you can either do this is the second method. You can do this, take a plot profile, but then you always have the risk that this is not perpendicular. So this is not perpendicular to the plane. So the best thing to do is take this angle tool, first plot along this lattice plane, then hold shift and then plot a 90-degree to this. Once you are done, put Control T so that your lines are drawn. Now you have two sets of lines. So these are your guidelines, or this don't measure, this is just for you to draw a parallel line. So I take from here to here. So now I know that my line has to be parallel to the line drawn. This is the purpose of this draw lines. So once I got a parallel, now I got a parallel line. Yellow line is parallel to the white one. So this just to show me take a parallel line. So once I get this done, I go to process this image and then sorry, I go to where you analyze and then plot profile. So I have here, you can see all the values. I don't want to, or I can, it's nothing matter of choice. So 4.45, 4.45 upon, you can count here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you have here by 15, this is the actual lattice spacing or the more accurate one as compared to this or the previous value. So you had here 0.278, the actual thing is 0.296. This is how we calculate. Sometimes what you can do is you can take this profile also and then plot it. You have seen some papers where they plot this profile and you can have either like you can put this at a good range of let's say 4. So you can plot either this one and uh, that's just a way to show. So what do these peaks actually show? This is a grayscale value. So as we know in computers, there's a 0 and 255 values for gray and white. It is black and white. So this one, white one corresponds to 255 and black corresponds to 0. So you have here white, black, white, black, white, black. So that's why we have here high value, low value, high value, low value. So this is how this works. And once you have it, after that what to do, you take this image, or I don't want to use this one but rather this standard image what I have. So I have this. Now I just in PPT or something you can draw, or either in image also you can do that in effect. But what I found is it's easier to draw or do things in PPT than image. So we put here, then take a text box and then write 0.296 nanometer. Or else better write it in angstrom because 0.296 doesn't make sense. 2.96 in angstrom, I'm just writing it, but you said the symbol. Okay, so how does this correspond to what do you say? Let's say a plane. I just show you. For that, you need a database, or in our high school we have something. I'll just retrieve one pattern. So I just got one pattern. It's a spinel pattern. So here we have DA spacing, right? How much did we get? 2.96. See, 2.95, 0 to 2 plane. So this was the pattern of the same material that we had. This crystal is spinel crystal or spinel or metal oxide in a spinel structure. So I took this one, and this is the 2.956, and we got here 2.966. So this is a reasonable value, and this is 0 to 2 plane. So you just plot here or write here 0 to 2. So that's it. Sorry, yeah, right here 2.96 angstrom, and you can put this or label this as 0 to 2 play set of planes, and this is the HRTEM analysis that we do in ImageJ. So the basic logic is you take an FFT of this, then take an inverse FFT, then calculate it. Okay, thank you. Have a nice day. Have a nice evening.